Hello?
Right. So,
Good?
you're on? Please go ahead.
One sec. Thank you. So just to jump right in, after my time here is up today, I hope you will be familiar with some key floor plan layout operators. And floor plan is, as he said, a DSL for describing the memory layout of a heap. So there's a syntax, which I will not get into the weeds about today, but you can look at the paper to see this figure. Instead, I hope that you will, after today, want to go back and read the paper to better understand the mechanics of a floor plan layout specification, which includes a denotational semantics defining what is and is not a valid heap instance given a particular memory layout, as defined by a floor plan layout specification. Instead, today I want to tell you how someone other than, say, a runtime system developer can benefit from implementing their own customized memory manager, and how Rust code generated from a floor plan specification fits into that picture, even while frameworks like Apache Spark and libraries like NumPy make their own trade-offs in the memory management design space. To be clear, there's a floor plan compiler written in Haskell that compiles into a core calculus, which you can find in the paper in Figure 10. The paper also discusses a general purpose memory management algorithm, IMIX, the IMIX garbage collection algorithm, which I'm glad to answer questions about, but will not be presenting today. And this is a diagram that you can barely see now of IMIX. And finally, I'm just generally interested in providing language support, which has really, really good performance. As discussed more in the paper, where I manually inspected the assembly code generated from the floor plan compiler. But first, I need to give you a little glimpse into the state of garbage collection research. Modern garbage collectors typically achieve good performance by being what is called generational. In a generational collector, heap objects are divided into regions of memory based on their age, where age is typically measured in the number of bytes allocated up to the current point in the program. And down here in this depiction, we see 8 objects have been allocated into the young space, at which point a garbage collection is triggered because we've run out of allocatable space. In the best case, what we see is our application will exhibit a high turnover rate, which means most of the objects marked with X's here on the slide will have died by the next time we want to do a GC. And as a result, we only need to evacuate, that is copy, a small number of objects into the evacuation region, which are objects O2 and labeled O5 here. At which point we can resume allocation, where we now start allocating into the space that we evacuated into previously. Over time, though, some objects will, as it happens, outlast multiple GCs, as is the case in the following example, where I've now decided object O2 has survived its second GC in what we call the young space. And as a result, we decide to copy O2 over into the first old generation. We do this because we can perform garbage collection on the older generations less frequently than we do on the younger generation, thus improving program runtime at the cost of some memory pressure in the event that, say, O2 were to now immediately die and therefore be taking up space for until the next GC of the old generation. And all is right with the world where performance is good, precisely because most applications that we see exhibit this allocation and lifetime pattern of objects. Except not always. On certain non-generational and specialized workloads, we get performance degradation. So for the remainder of this talk, I plan to describe the following 3 characteristics of an application which can result in degradation of performance of a generational garbage collector. And in doing so, show you how language support in the form of generated memory interfaces can reduce the burden of implementing a customized memory manager for tackling these performance constraints. Now, imagine you are a data scientist analyzing streams of data where each data point is some fixed width record data type. Oftentimes, the analysis you do over this data approximates some property of the entire data set by performing some calculation over the current snapshot of the data that you can see. And the trade-off you need to make here is to maximize the window size so as to improve algorithmic accuracy without incurring so much runtime that data streams in faster than you can process it. For example, both the k-means algorithm as well as an algorithm that I looked at, annotated down here, approximating the entropy of network packets, both exhibit accuracy which is proportional with the window size, and therefore also, unfortunately, proportional in the size of the heap. This trade-off constrains us even further when the data representation chosen for us either wastes space, as I've indicated here in this old generation with dashes being these segments being some wasted space, and or the default GC policy incurs a per object overhead in order to both scan and evacuate these objects into the old region. That were, even though these objects might have been destined to survive multiple GCs regardless. And so that copying is extra runtime that we would like to save. So let's look at a more concrete example. Here on this slide, I've implemented a Rust interface for the in-memory representation of, let's say, a Bluetooth packet. We have, this code looks typical. I've defined my types up front, where on that third line, the adder type is synonymous with a word-sized pointer value, which in Rust could be a star mutable U8, for instance, pointer. And I've also, now in this segment of the code, I've computed the offset to each of the fields in our Bluetooth packet in terms of one another. We have, for this example, an identifier, say, is a data sink collecting these packets, identifying that sink. We have the epoch, namely the time at which the packet was measured, a MAC address, a RSSI power value, and then the data, which is a 13-byte array of just what the Bluetooth packet contained for data on the airwave. And finally, with those values that we've computed to get to the offsets of those fields, I can define getters and setters for accessing them. Well, this style of interface already exists in real systems like this one here, exactly when precise control over the layout of memory is needed, as is the case in this JVM snippet of code, where this is actually in the runtime system of a JVM. But as it turns out, that code is buggy and error-prone to write. And in fact, that exact code on the previous slide here, you'll see is basically duplicated here in this GitHub issue, where there was, for quite a long time, an undiscovered bug due to a variable mix-up, where someone computed the offset to the status word of an object in terms of the type information block, tib bytes, instead of the number of bytes in the status word itself. So even though it takes time to manage these sorts of data interfaces from before, when done correctly, their presence arguably improves code structure and legibility, which also happens to be why my advisor and I chose Rust as our target language, which was to leverage its type system, which I personally was introduced to at a talk last year in Boston, Splash iTalk, which in part spurred the fact that I wrote this compiler targeting Rust. But come on, I'm lazy sometimes. This code is clearly very mechanical and has all the hallmarks of boilerplate. Why can't I just generate it from, say, this code? So this is the first snippet of Floorplan code I'm showing you. And that's exactly what the language support we've developed, Floorplan, does. It compiles a declarative specification of a memory layout into all the type-safe abstractions that we genuinely want to use, but currently have to write by hand. However, if all we got was a pile of fixed offset getters and setters, then, well, we might as well just stick with structs, which is basically what this code is defining here. And a struct like memory layout is, I'm saying now, the most basic thing you can write in Floorplan. So let's get on to our next example, because that's fairly simple. In our domain of, again, window-based streaming applications from before, data typically comes into view by way of a window sliding policy. And where the traditional window sliding policy is just to retain a fixed number, say n, of the most recent data entries that we've observed from whatever source we're reading from. Which might look like this, where we have 100 entries marked as allocated A. And what we need to do to manage memory is evict old entries as new ones come in, like so, where we've inserted 3 allocated entries, freshly allocated, at the end of our window and have now marked the oldest 3 entries, the first 3 here from time 0 to time 3, as free. But implementing this naively as a result of the GC will incur excessive overhead because a FIFO queue is, for the garbage collector to know that all the objects are in a FIFO queue are live, it needs to actually scan every single pointer, incurring a fairly high overhead. What we really want for the GC to do is to treat that data structure like a ring buffer in the common case, which exhibits constant time allocation and eviction, but to also support an arbitrary eviction policy where in this example at time t equals 4, we've retained this data point, but it's not actually part of the queue. So we do just implement a 0 copying customized allocator, where in this example it's just a sequential array of bytes here, delimited by messages, which that avoids some of the bookkeeping costs and copying costs that are typically associated with many generational implementations of generational garbage collectors. And on this slide, I've implemented the initialization of such a desired customized memory manager memory layout. First, at the top here, we initialize access to some out-of-core data structure, where in this case I've just used the file system in this example, as well as we're computing the size of the heap in terms of some integer number of megabytes that we want the heap to be. Then we can, in this next snippet, anonymously mmap a region of virtual address space with which to allocate objects with the proper alignments as we are computing here to support certain bitwise operations later on when we want to look up things inside of these blocks. Next, we iterate through the entire heap's address space, carving up that whole mmapped region into blocks, which will subsequently contain individual Bluetooth message packets, which is initialized by this block : new method that I will not go into here. But finally, we just generally will construct some controller data structure with which we can track memory management related bookkeeping that we initialized earlier. Now, this code is from the center, from the previous slides. And I've highlighted specifically the 5 memory layout operations that are being performed by that code, which is what Floorplan will tackle here. And instead, now we can write a declarative layout specification and get out an interface supporting statically typed versions of the exact same operators. Those operations get associated with these highlighted generated address types, one for each floor plan declaration, where we've declared a heap as a floor plan decal and another block declaration, such as we get out this block adder data type, and those data types are essentially just small, no overhead wrappers around pointer types that the floor plan low-level code can operate over on its own without you having to operate directly over U sizes in Rust or star mutable U8s. But also we have this heap end adder type, which points to, in general, the first word of memory past the end of the type that it's defining. And the first operation from this code is a line up to block, which gets generated as a member function of the heap adder type, because first off, the first thing in a heap is a block, and two, that first block has a 2 to the 21 byte alignment as well as size, as indicated by this, what I like to call the @mag operator, because it's defining it has to be aligned at this value and also have magnitude that size. The second operation that I'll show you is init_end, which gets generated because a heap is defined to be any number, 0 or more blocks. This is what the pound operator here is doing. It acts exactly like a prefix notation Kleene star operator in regular expressions. In contrast, the pound operator inside of our block declaration, which is grayed out here, is bounded to 2 to the 21 bytes, and so its init_end function that gets generated, which is not shown anywhere here, does not have to take in an unsigned integer parameter, because the floor plan compiler can compute how to get to the end of a block without doing any sort of iteration or asking the user for the value, the programmer for the value. This next operation, which is the same one in 3 different places, skip to next block, gets associated with the block adder type because blocks in a heap are iterable, as with the pound operator I described before. And lastly, we have an isAfter heap end function, comparison function, producing the Boolean you would expect, as it's, if we were to look in this code, it's just a greater than operation comparison. And that gets generated for the block adder type relative to the heap end adder type, which is the first parameter that gets passed in, because a heap contains and ends with iterable blocks. If we had instead put some metadata at the end of our heap, then this function would have a different type in that it wouldn't be able to compare with the end of a heap, because the last thing in the heap is not a block. So hold on. Just to be clear, I wrote all this code myself, and you may be thinking, why am I writing this low-level code when there exist frameworks like the one I talked about earlier, or mentioned earlier, Apache Spark, which will do this for me? Spark itself achieves good performance by hiding data entries from the garbage collector, as is the case in this code. You don't have to look at it in too much detail. This is a snippet of the heap memory allocator inside of Spark written in Java. And what I'd like you to focus on is this line 22, which is where they're actually doing their memory allocation. And that is where data is allocated into enormous Java native long arrays, which entirely avoids the need for memory reclamation by the JVM garbage collector itself. And well, once you've decided to go this route, where your memory abstraction is just a raw array of bytes, you're essentially back to square one in terms of language support for memory layout, which must be built from scratch by the developer implementing all your logic, be it in Java, C and C++, or Rust in our case, which has Floorplan now. But wait, I forgot one language, for example. What if we wanted to implement some memory management in Python to optimize, say, the import of our data to speed that up? Because after all, I am talking about scientific analyses, and how can I leave out Python in that case? And that's, as it turns out, exactly what the NumPy developers did here in this chunk of Python code. And so, among other things, we'll just focus on this. Go ahead.
5 minutes.
Okay. Which this Python code manages data layouts to support proper mmap alignments. But not every file format or memory layout is obvious from the code that implements it. Instead, we're left writing notes to our future selves, like this one described in the NumPy NPY file format, the design decisions of our layout. And so with Floorplan, instead, you can write down these otherwise unspecified relationships among pieces of memory that are not formalized elsewhere. And to drive home the point, actually, I'm going to skip over HDF5 to save time. It's a little bit about TensorFlow that I tried to use, but then jumped back into Rust. And so I'll talk to you about the third way of implementing these things. For example, we might want to be able to ensure from our example before that all of our allocated objects in our window are fit into exactly 2 system pages at most, where I'm talking about this, just the queue part and not the retained data. And to do that, we would first need to write code which figures out which messages in a block are free and which ones are allocated, as is done in this handwritten Rust code. This code computes the address of the nth bit in a lookup table located at the beginning of the block, where up here I've defined individual bits, those really close together lines, and then all the 8 objects that those bits correspond to. For example, in this one, where the highlighted 04 object maps directly back to the 4th colored bit in the bitmap. And the address of that bit is represented in the return value as an 8-bit mask, where the U8 return, which is the U8 returned by this function. And that mask, when you get it back, applies to the value found at the address represented by this usize returned. A key insight we had with Floorplan, now I'm showing you this final bit of Floorplan code, is that memory relationships between discontiguous pieces of memory can be described as a non-context-free grammar, which is implemented in Floorplan as formal parameters representing non-negative integers, repetitions on pieces of memory, like with this variable k, where we've brought k into scope, and then we're saying a lookup table contains k bits, and importantly, it contains the k messages that those k bits map back to. From this spec, the compiler generates all the necessary array-like operations, where so before we had all these memory layout operations written in terms of just low-level Rust bitwise operations and pointer arithmetic, whereas now we've encapsulated all that into these array-like operations. And so as before, this includes some basic field accessors, messages, and lookup to jump to those offsets. And we have this getContainingBlock function, which gets generated because messages are defined to be inside of a block, and so on, where we can compute the other array-like operations, such as getting the index of this pointer, which is now a message type, from the base address of relative to the base address of the messages array that we've defined in this portion of the Floorplan code. We can also discover, this is just basically an array access operation. We can compute the address of the nth thing in our lookup table. And as a bonus, we get a bit mask data type for selecting just the bit we care about, where this could be something like OB1 and then all zeros to indicate the highest level bit in that lookup table for that kth particular message that we care about. And so that's Floorplan, except for a bunch of linguistic things that I did not talk about that you can look at the paper for. And instead, today I showed you that a memory layout is only as precise as the code and type system that implements it, which is why, regardless of all the ways custom memory managers wind up being misapplied, a number of which are listed here, the difficulty associated with implementing pointer types should not be a valid argument against doing your own layout customization. Thank you.
So we have questions?
Yes?
I saw that some of the Rust code you had was using raw pointers and unsafe blocks that compute offsets. Is that code that you generate
So
with
the,
unsafe blocks?
yes, so the code, a lot of the code that gets, actually in this case, I believe none of these have unsafe in them because they were just arithmetic operations that aren't actually accessing memory. But some of the code before does in fact, yes, require wrapping it in unsafes, such as, actually I'm not sure I even showed you any of those, but yeah, there are like the getters and setters that do get generated,
Right.
which look a lot like the, at the very beginning,
Right.
do require the unsafes.
Right. So, do you know if you ever get close to running into undefined behavior there?
Any what?
Undefined behavior. So if you break the guarantees of the compiler in these unsafe blocks?
Yes, you can certainly do that, but that's once you're at trying to implement your own customized manager, you're kind of out of luck in terms of getting this safety back in the first place, is a takeaway we had from this.
So did you have to worry about this, or does the user of Floorplan also have to worry?
The user of Floorplan also has to worry about the unsafety because they are themselves deciding which piece of memory has what type. For instance, if you can change the type of this A to an F, and that'll result in a different offset.
Okay.
So, what's missing now for me to be able to take Floorplan and maybe some additional bits that says yes or no? I want this to be able to access, to be accessed in parallel, and then be able to write, to just specify my own custom memory management system for my own personal favorites, data type, maybe with some restrictions as to what I can do this for, and then have that work with the rest of the garbage.
Could you repeat that? Sorry, I didn't quite.
What's missing now that I can just take a Floorplan specification and a flag maybe about concurrent access and have the system generate me a custom garbage collector just for my, optimized for my special data type? Is that even feasible with the answer that you just gave?
Well, you'd have to implement the entire GC policy in the first place in terms of all these layout operations, in which case you could just parameterize the type to pass in that type for your particular size, but that might run into issues with if you want to be able to pass in, say, the messages I was showing here are exactly 32 bytes. So a lot of this layout was designed with 32 bytes specifically in mind. And so I think the whole point in the first place is that you want to customize it to the data type that you're getting. But if you could imagine, say, someone wrote a collector in terms of Floorplan, and then you could get a much more constrained set of types that you could pass in to get that to operate over your own data structures.
All right,
Thank you.
good, thanks.
Thanks.